Okay, so let's get started. And what I want to share with you is now, first, I would like to know how to prepare your homework 4. And after reading your reports about the homework 3, there are some very interesting points, and I would like to share with you. And then I will go further about your homework 3 reports, because I found that none of you train a model for action recognition. Most of you train models for image classification. Okay, but so the difference is, I will say it later, because images are 2D data, but the actions or videos are 3D data. Okay, so both of them can be recognized by convolutional neural networks, but one, for most of the image classification, we use the 2D convolutional, but for action recognition, we use 3D convolutional. So this goes, and finally, I will show you something about the generative model. It is highly related to your homework 4. Okay, first of all, I would like to, I should say, last week, I heard that when you log in our server, you will get different GPU models. So I don't know how to explain it, and I'm waiting for some screenshots so that I can share those data with our server admins, so that maybe we can try to solve the problem. Because some of your algorithms may need consistent GPU models. But however, since I can log in the system, so I try to figure out what models or what machines they have. So this is my finding. Okay, so because I create a experimental student account, all of you have a student account, right? I can create another one. So after logging the system, I use some Linux commands to list. So I found the server my account was using, it has 2 CPUs, and each of them has 18 cores. It means 36 threads. The total, there are 72 threads. And the overall memory size is more than 1700 giga, so it's quite large. And there are 8 GPUs. Each of them are Tesla V100. So because some of you told me what is the model? R6 8. So I'm wondering, maybe we are using different servers. I'm not sure. So I need to confirm with our admins. I know at least there are 2 servers, one for students, another for their internal researchers. Okay. And okay, so I checked the spec to run Easy Diffusion v3. Easy Diffusion is the model I recommend you to use because it's very easy to install the program software. So it requires at least 2 giga. So because our server provides the model is at 16 giga, so it's sufficient to run the Easy Diffusion 3 and 8 giga memory. So since we have more than 700 giga memory available, so you can allocate as much as you want. And 25 giga hard drive is easy. So we can easily allocate that. Then, okay. So I recommend you use the setting. The setting is my account uses 32 giga memory, 4 CPU. In fact, the CPU means threads because for Linux machine, 1 CPU just means 1 thread, and just 1 GPU is enough. A few weeks ago, I tried the setting, use 8 GPUs. So, but I found it's very difficult to get 8 GPUs simultaneous because if we only have 8 GPUs and someone else is just using one of them, you have no way to get 8. But however, to run programs for your homework 4, just 1 CPU is enough. Okay, so and it's easy for you to just get if you just need one GPU. Okay, so I use the setting to run diffusion model and get the result. So this is important for you. If you can have one GPU, one is enough. You only need 3 to 10 seconds to generate an image. However, diffusion can run on CPU, but it's very, very slow. I use 55 minutes to generate the same image. So it's time consuming. If possible, just get one. Okay, and then there is a problem is I have to mention. If you just log in the system and use the default Firefox, the version is 18.6. There is I don't know, there are some incompatibility problem. When you launch Diffusion, you will see just a message, stable diffusion is starting. Then there is nothing keep going on. So, but however, the latest Firefox version is 119. If you update your Firefox to the new version, everything is okay. Okay. The problem is we are using the Q4 system, and the Q4 system is a Docker-based system. Every time you load the Docker image, your default Firefox browser will go back to the 18.6 version. So how to solve the problem? Okay, you can update, you can either update the Firefox every time. It's feasible, no problem. It's very easy. How to do it? You just go launch your Firefox and click the icon here and go to the help and go to the about Firefox. And you will see a restart to install Firefox. Then just click it. Then your Firefox will update to the latest version just by one clicking. But the problem is every time you need to do it again. So so I use another solution. I just install another copy of the latest Firefox to my home folder, because you know the home folder, it is mounted by a real SSD. Therefore, every time after logging into a system, I can use the latest version. Okay? And how to install Firefox to a Linux version? You can just follow the instruction from the Firefox official website. Okay? And it will like this. After following the instructions, you will see a new icon on your desktop. Okay? Okay, then you can, under Easy Diffusion for your homework 4, just following the instruction, go to the Easy Diffusion website and download the files to your Docker instance. Okay. This so I list the instructions here, and it takes me, I tried it 2 days ago, and it took me 1 hour to finish everything. Okay, and then this is the port 9000 conflict problem I mentioned a few weeks ago. So let me talk about it again. So it means because we are using a Docker image, and there is another process using the port 9000. And the Easy Diffusion's default port number is also 9000. So there are 2 solutions. One, you can kill the existing process using the port 9000. It is this. It is a PHP-FTN program. It's something related to the PHP server, but I do not fully understand what is the process, and I try to kill it. Nothing wrong. I can still do almost everything at least for my homework 4. And another solution is you can just slightly tweak the port number. The port number is written in the config.yam file. So this is the where just click it, then just change it to another port, say 9001, because the port is not used by any existing process. Then every time when you log in the system, then you can use your easy diffusion very easy. And okay, because of the Firefox problem, so there is another setting. Whether you will open your browser on startup, the default setting is true. But here I change it to false because after installing another copy of Firefox, I will have two copies of Firefox in my system. One is the system default. This is in the Docker image folders, and it will be restored every time. Another is on my own home directory. So since I prefer use the one in my home directory, so I turn the option from true to false so that I will not launch the default Firefox browser. Okay. Then after launching my own latest version Firefox, I can go to this URL, and this is the web UI to access the easy diffusion model. Okay, so please note here, this is HTTP, not HTTPS. If you use HTTPS, you will see nothing. Okay, and there are some online tutorials teach you how to use easy diffusion, and they are instruction based.
Drawing style basically is just the type of art you want. Cell prompt here. It's just half-body portrait of a steampunk woman. Very popular topic to generate images with. I also have my negative prompts here that I've already inputted. I'll put a link in the description below for this as well. And to demonstrate the modifiers, I'm just going to use Stable Diffusion 1.5. I'm going to use Euler Ancestral image size of 512 by 768. Step.
So there are also some
well, hello, good people. A few of you have asked me to cover VAEs and LoRa and easy diffusion, so that's what we're going to cover today. So let's start off with VAEs. What it stands for is Variable Auto Encoding. Simply, they make your images more vibrant, more crisp, and they could even improve the details of the hands and faces. Nowadays, a lot of models have them baked into the actual CKPT or SafeTensor file, but some models will still suggest for you to download certain ones. For example, if we go on to Civit.
So, so here
steps we'll leave at 30 to AI.
Okay. And if you need online documents, so you can go to the Easy Diffusion's official website. There is a wiki page, and there are a lot of instructions or explanations what of each component work. Okay, and there are some online model sharing websites. You can download those models to your local machine. I mean the Kubeflow system. Then you can create different styles or different topics. Okay, so there are a lot of platforms. Easy Diffusion is just this one. So what's the relationship between Easy Diffusion and Stable Diffusion? In fact, Easy Diffusion is a package. It helps users easily install the Stable Diffusion and make the user interface, simpler. Okay, because so that once you are familiar with Easy Diffusion, if you want to try some advanced topics, you can try Stable Diffusion. It is slightly more complex, and the installation instruction is also more complicated. But if you are interested, since you have the computational resources, you can do. If you are interested, try it yourself. No, okay. And otherwise, you can also try the Dream Studio. Okay, so let's see. Dream Studio is like this. It is a website based. Okay. Okay, Dream Studio, right? And okay, so that, right? And okay, log in. See. Okay, so this is a prompt. You can try any prompt you like. So, like what? Okay, so the classroom of computer vision, 20 students. Let's see what will generate and generate. Okay. Then let's see the results. Alright, okay. So you generated 4 images, each of them matching the prompt. But however, okay, so you are doing the same thing to create the images. The only difference between, I should say, the major difference between Dream Studio and the Diffusion is, if you run Diffusion, you don't need to pay anything. But if you try to create images on Dream Studio, then you need to pay the coin. So I have 23.2 coin. Once you register as a website, you get 25 points. And every time you run, you need, for example, I need 0.91 point to generate the 4 images. Okay, so and you can try a few times until you run out of the points. And if you run out of points and you still need to generate more images, you need to pay for it. So that is the only thing. Because generating those images requires GPU resources, and they are not totally free. Okay, that's the reason why I recommend you to use our Qflow system, because it is free. You can generate as many images as you like. Okay. Alright, so there are many other platforms you can try, and the Dream Studio and our Diffusion, their backbone algorithm is the same. It is a stable diffusion algorithm. Okay, and even though you can try Microsoft Edge. It contains a bin, and the bin can generate some images. So also ChatGPT-4, there's no problem. Okay. So let me see. Okay. All right. Okay. So let me see. Actually, let me show you the live demo. We will talk about it later, but let's try to do. Okay, so I just log in our Qflow system, and okay, so this is the user interface for the Easy Diffusion. See, the latest version is 3.0.6, and I can just create 4 images. When you just load the when you just load the program and Okay, so there are 4 images. So you can see it takes 9 seconds to generate the 4 images, quite quick. Okay, and you can try anything. Just what would you like? See, what do you like? Okay, let's see. Fish, goldfish. Okay, and let's try to create 4 images about goldfish. Okay, so there are 4 goldfishes. So it's for the label of a user, it's very easy to use. And the online tutorial will teach you how to add some modifier. For example, if I want to create the children's drawing style, okay, and then I add the image modifier and let our program run again, and I will generate another set of images. But however, something wrong. You see there are 2 eyes on the same side. So, okay. So that's the interesting part of your homework 4. Try to explore any images you would like. Okay. So if I say what is images you like, let's try something. Let's try our school. And let's see what will be generated. Okay, so these are Chang University, right? Okay, so okay, it created something, but it may not be the images you imagine. Why okay? I don't know. Okay, so that's the reason why text to image, I should say, generation is still a very hot research topic because it is not perfect. You try to create some images, but it is out of your expectation. However, I want to show you, the computational resources are available. Try to use it if you don't want to pay, or if you want to explore the possibility of the system. Okay. And there are not only just one system. Easy Diffusion is just one, which is very easy to install. You just need a command. Okay, you can launch the system. All right, so let's talk about something interesting about your homework 3. So first is batch normalization. Okay, so do you remember? This is the slide shown by your classmate, Miss Zhao. Okay, so let me repeat what she wanted to do. She created a neural network, and she tries to use the neural network to do the CFAR10 image classification task. Okay, so this is the architecture of her network, and she got a performance about 75.93% accuracy. And then she tries to improve the network architecture, and she found, okay, there's layers named batch normalization. After adding the batch normalization layer, she improves the performance from 75.93% to 82.5%. Okay, so it's very useful, right? But what is the batch normalization layer? So I would like to, okay, so one of your another classmates, Mr. Liu, he tried to develop a embedded system so can recognize users' facial expressions. Although he only set 4 different expressions, neutral, happy, sad, and angry. Okay. When he tried to train the model, he found, okay, they are important hyperparameter is the batch size. Okay, so the two things are all related to batch normalization. Mr. Wang found he should add the batch normalization layer and improve the performance. And Mr. Liu, he tuned the batch size. It is also a parameter for the batch normalization to get the best result. So let's see what the batch normalization is. Okay, so let's recall. This is our convolutional layer. Given one input image or just a feature map, okay? Through the convolutional layer, you will generate several feature maps, okay? And because our computers can process multiple instances at the same time, so it will like it. You still have the same filter bank, and now you have 2 images as your input. So you will generate 2 sets of the output feature maps. Okay, when you change the number of 2 to n, so it will like this. You will have n instances for just the same convolutional layer. And each of the instances has C-in channel, and each of the images, the width and height is H and W. Okay, with the same filter bank, you will generate a set of n feature maps. Each of the feature maps has C-out channels, and the new resolution of those channels are H prime and W prime. So this is called a batch of output. And the batch normalization means, okay, for those channels, I want to do something to translate those values to a new presentation so that the means of those values will be 0 and the standard deviation of those values will be 1. So this means normalization. Okay. So normalization, we just want to normalize those outputs so that we can control the mean and the standard deviation. So the paper was published in 2015, okay, and the authors of the paper, they claimed it can help our convolutional network to converge quickly, and they claimed the reason was batch normalization can help reduce internal covariant shift so that it can improve the optimization process. Okay? But however, I will show you. So let me explain what the internal covariant shift is. It means, okay, when we train the neural network, we change the parameters, right? After every backpropagation, the parameter changes. So that it might have one thing might happen. When you have a set of input image, okay, and your convolutional network, it will generate a set of output results. Okay, so since if the green curve is the original distribution of your result, after changing some of those parameters, your output results may change. So this is called covariant shift. Okay? And if it happens when you keep changing those weight parameters, okay, then it's called internal covariance shift. So like this one. For the first layer, okay, you have a certain distribution. And after the first layer, you will go to the second layer. And the distribution of the output of the second layer, it may change. So through different layers of convolutional networks, your final output result might be very different from your input results. Okay. However, okay, this is just the claim of the paper in 2015. Okay. I would like to say why we need normalization. Okay, just imagine a case. Say you have an algorithm or something else, and the algorithm only needs two input parameters. One is age, and another is the customer's assets. Okay, so imagine the scales of the two input variables. So because the x variable is age, so what the normal range of an age is around maybe 18 to 99. Okay, but another input variable y is the assets. If we measure the assets in terms of New Taiwan dollars or US dollars, no matter how, the range of the value, it might be 0 to a very, very large number, or even negative value to a very, very large number. So the range is very, very large. When the range is very large, when we do backpropagation, so what will happen? It means if you just slightly change the age, okay, and you may generate a very big difference in your output. But for another input variable, the assets, because the range is so large, you only change it from add a slightly value to this input variable. Your output result may not change a lot. Okay. Therefore, when you do backpropagation, it will be very sensitive to one input variable and insensitive to another one. Therefore, you might see your optimization progress or your static gradient descent or something else. It vibrates here, there, here, there. After normalization, it will make the variables more equally contribute to the output result, so that it can help create something more smoothly, more easier to converge for your optimization. All right, so here is the history of normalization paper. First, the paper normalization, it was published, it is uploaded to the archive website in 2015, February. And it claimed, the normalization layer can reduce internal covariance shift. Right, and the paper was published in ICNL 15. And one year later, the Hinton group, they published another paper called layer normalization, and I will show you what's the difference later. And in 2016, our reference book was published. And in 2018, there are 3 papers almost released at the same time. The one revisiting small batch training for deep normalization. This paper was used by your classmate, Mr. Liu. He read this paper and use the finding of this paper to tune his batch normalization. Okay. My finding of this paper is if you use a smaller batch, you may generate a better result. Okay. However, this paper was only uploaded to the archive, and it was not accepted by any major conferences or journal. So they claim the findings, but if you were, because you are graduate students, you may doubt it, whether it's true or not. You may do experiment to validate or refute its claim. And then 1 month later, there's another paper uploaded to archive, and the paper was accepted by NIPS 18. Okay, and another month, there's another paper uploaded to archive and accepted in NIPS 18. Oh, NIPS, do you know NIPS? Now it was renamed to NERPS IPS, I forgot the full name of NIPS. Let me check it. NIPS. Okay, so what's the full name of NIPS? Neural Information Processing Systems. All right. Okay. So this is the best conference for the neural networks. Just like CPR is the best conference for computer vision. Okay. So so it means since the paper was accepted by the NIPS conference, usually it means the quality of the paper is very high. Okay. So see the two papers, both of them were accepted by NIPS, and both of the two papers they claim no. The batch normalization works, but it is not related to the internal covariant shift. So this is a very interesting finding. And then there's another paper, how does batch normalization help optimization? And the subtitle is no, it is not about the internal covariant shift. It's directly claimed that they are unrelated. So this is a very interesting finding. Okay. And this paper was accepted by another conference, all right? Then the NIPS 18 took place, and in 2022, our textbook was published. So when you read, when you read our reference book, because it was published in 2016, so there's no way to know the following papers. But however, in our textbook, yes, because it's newer, so it mentions those important papers. All right, so is this okay? Okay, let's go back to the first paper about the batch normalization. Okay. Okay, so in 2015, the state-of-the-art classification algorithm is Inception. It is GoogleNet. Okay, so they use GoogleNet as their baseline to do experiments. After so see this curve. This curve, the dotted line curve means if you use GoogleNet if you train GoogleNet on the ImageNet data set, then you will need a lot of time. So the x-axis, in fact, is a step. Do you remember? When you do backpropagation, you just do one step, so your gradient will go slightly slower, or your total loss will go slightly slower. So it means more than 30 million steps to achieve a certain score. they say the score is 72.2%. And they found if they add batch normalization, they insert the batch normalization into the inception net or Google net, then they can accelerate the optimization speed in terms of what? Okay, so the pink dashed line here is okay. They just insert the brown dashed line. If they just insert the batch normalization, okay, they can reduce the training step from 31 million to 13 million. So it is a huge improvement, okay, and achieve similar accuracy. And then the BNX5 means, in addition to adding the batch normalization layer, they can slightly tweak the learning rate. The learning, do you still remember? When we do the gradient descent, there is learning rate. It means how much we will move from the original point to the new point. Okay. Usually the learning rate is a very small number, say 0.0001 or 0.0001, etc. So after adding the batch normalization layer, they slightly enlarge the learning rate by 5 times or by 30 times. So it can further improve the optimization process. But you see here, if they set 5 times, they only need 2.1 million. If they set 30 times, they need further more. Okay, so that's the reason why the larger learning rate may not be the best choice. They need to tune the parameters. Okay. And the last one is if they enlarge the learning rate, but also change the activation function from ReLU to sigmoid, then what will happen? They found they will never reach as well as the accuracy. Okay. But how? Right. Okay. Let's take a break, and I will continue the slides in next class. Okay. All right. So from their experiment results, you can see when they set a very large learning rate for say 30 times, they need more steps to converge. Okay, let's go back to this slide. Okay, it's very similar to this case. When we use a very large learning rate, then we will I should say the optimization progress may go too much, go too further, and go to another position that is not a local minimized. So that is to go to there and go back. So it generates some vibration result like this. Okay. Therefore, from the experiment we see if they use a very large learning rate, I guess their optimization vibrates, so that they need more steps. Okay. So from this NIPS paper, they find, they claim the real reason batch normalization helps optimization is batch normalization suppress the very, very large gradient value. So from this chart, okay, the left chart means if you use batch normalization, then pay attention to a number. This is 0, this is 0.2, and this is 0.4. They are small values. And if they do not use batch normalization, then the magnitude of the gradient, this is 0, and this is 2, and this is almost 4. So C2 compared with 0.42. So the difference is 100 times. Okay, and let's see the chart. See the y-axis. So the y-axis, the number of those gradients are, most of them are 0, because you see the number is around 24K. But if you use normalization, okay, the top value is also 0, but the number of those gradients are around 2.4K. So it means if you use spatial normalization, the distribution of the gradient point, it is like well distributed. Most of them are small numbers. But if you don't use spatial normalization, it means the original Google Net or something else, then you will have the I should say heavy tail distribution. It means most of them are concentrated to the 0, but some of them will be very, very large values. Just because of the large gradient values, the optimization process will vibrate somewhere here, there, and after. Okay. All right. Now we have the theoretical concepts and how to calculate spatial normalization. Okay, let's go back to this slide. If we have a batch of input layers, the number of batch is n, and each instance has C in channels, and the resolution of those channels H times W. Okay, and this is our output result. Then let's take a look at this figure. Pay attention to the C out. This is the number of output channel. Okay. Then we see. Suppose this is a number of output channel. We use another symbol D. Okay. And for all other dimensions, no matter it is number of input instance or the width or height, we just see them the same. Okay, so there will be n. N means n. The new, okay, this is a simple abortion, but the meaning is just view them as a two-dimensional matrix. One is the number of output channel, and another one is all other remaining channels. Okay, then spatial normalization is just we compute the mean along the C out. It is if we have 6 output channel, then we compute 6 means. Each of them is the average of the n numbers, and we also calculate its standard deviation for each channel. So this is a channel by channel normalization. Okay, and then we can use the easy minus operation and division operation to generate the new values. The new values x hat will, the mean of it will be 0, and the standard deviation of the output will be 1. Okay, so this is I should say it's very straightforward. Okay, but however, if we just use the the standard deviation, I should say normalization, then how can we learn something from our training process? Okay. So the authors of the spatial normalization, they introduced 2 more weight parameters. They call it as gamma and beta. So when they generate the output of the spatial normalization layer, the gamma and the beta will be applied to the standardized x hat and generate the y output. So beta and gamma, they are learned parameters. if gamma just equals to the standard deviation and the beta equals to the mu, then the input will be the output. Nothing changed. Okay. But okay, now you see the mechanism. It's very easy. Just introduce a few new parameters, and you can calculate the mean and the standard deviation when for your training phase. But however, when your test phase, if it just as image as your input, there is no batch. So how to solve the problem? So the authors of the personalization, they proposed, okay, when they train their new networks, there are several layers, right? When they train a batch of input images, they will keep the mu in their memory system. So they can learn the mu as a rounding average. It means if you have 1 million batches, then you will do the normalization 1 million times, and you can calculate the average of those 1 million batches. Okay, the definition of rounding average look like in the beginning you set the mu zero as there, the mu value as 0. Then for each iteration, okay, you slightly update it, slightly update. So it will. They use the mu test as the output, as the mu value for the test phase. All right, so now you have mu, you have sigma, and then if for the test phase, no problem, you can do the same. You can repeat the same benchmarkization step. All right. So usually we will, okay, they propose to fuse the benchmarkization or insert the benchmarkization after a fully connected layer and before the activation layer. So how many fully connected layers you have, how many benchmarkization layers you can insert. Okay. And okay, there are some properties of the personalization. First, it makes the deep networks easier to train. Okay, let's recall the figure here. Because of the property of personalization, there will a lot of gradients. Their values are very small. Because those values are very small, the training process won't, I should say, less vibrations will happen. So that it can make them easier to converge. And okay, because most of the gradients very are small, so we can use a higher learning rate, just like the experimental result shows. And the network can be more robust to generalization. Okay, because sometimes we will train the network from scratch. It means all of the learnable parameters are random numbers. So with personalization, because since the gradients can be much smaller, so it is easier for us to use the random number generalization. And they can regularize the result, actually the process in the training. And very interesting is you just add a few new parameters. So the overall cost is very, very small in terms of the whole parameters. But there is I should say, since we use rounding average as to learn the mu and the sigma when the training process, it may not be the case of the test image. So usually that might be the bug. But I should say, we cannot guarantee it, but we know theoretically there are something we need to. Okay, so I just mentioned. Actually, let's go back to this slide. This is the history of batch normalization. So after the batch normalization paper was published, 1 year later, Hinton's group proposed the layer normalization. And now let's take a look at what a layer normalization is. Okay, when we do batch normalization, so see this is a very big metric, right? There are only number of channels, output channels, that is n, and all other d, and all other elements are n. So we compute the mean and the standard deviation of n, so that our n, those numbers becomes 1. We treat them as just a single dimension. And layer normalization do another way. It keeps n unchanged and normalized with respect to the number of channels. So this is layer normalization, and all other things are the same. But however, you can imagine, for convolution networks, usually we have relatively few channels, say 10 channels or 5 channels or 30 channels. But we have a lot of numbers for the number of instances. For a batch, we can usually say 32, 64, 126. And they are also width and height. So usually n is a very large number, and d is a relatively small number. So that's why layer normalization is a very intuitive way to normalize the batch of data. But the layer normalization, the method do it another way. They normalize the d. D usually is small, but however, the method can be used somewhere. Usually, we don't use the layer normalization for convolutional network, but it can be used for RNN or transformers. And there is another normalization called instance normalization. Okay, now we see the 4-dimensional batch. The number of n, channel, width, and height. And the batch normalization means we keep the same number of the channel. We learn the mean and standard deviation for each channel. But instance normalization means we not only learn C, we also learn N. So we only normalize the width and height. Okay, so you can see now we need to learn a lot of mu and sigma. Therefore, we will have a lot of gamma and beta. Okay. If we draw them as a chart, it will like this. So this is in the batch, there are 4 dimensions. The number of instances, the number of channel, and also there is the resolution. The resolution is 2-dimensional, actually, and the height and the width, but we can treat as just a 1-dimensional factor. Okay. So batch normalization means we normalize everything along the dimension of channel. And the layer normalization means we normalize data with respect to the number of instances and layers. And instance normalization means we normalize those data for every instance. Okay. And in addition, there is even a group normalization. It's something like a layer normalization, but it do not normalize it for all channels. It's only normalized for some selective channels. Okay, now the next question is, where is instance normalization used? Okay, take a look. This is instance normalization. We normalize every input instance. Okay. So for 2 different instances, we will normalize them one by one. Okay. Where is it used? So this paper published in CGU 17. It means So the title is Improved Texture Networks. So it looks like this. Given an input image, you want to learn some texture style. So this is the input of the panda. And for different reference textures, you may generate this image, or this, or this, or this, or this. Okay, so it is very similar to our homework 4. We aimed to generate some images, but a few years ago, they don't have the text prompt. They still use the style transfer given an input image. They learn a network. The network can generate another images. The structure is still the same, but the style is different. Okay, so how to describe the style? They use texture. So the textures in the input images are different from the output images. Okay, so they learn some models to do the texture or style transfer. So this is another case, given the input images. Because they learn or they train their models from different architectures or reference images, they will generate a different output style. Okay, so let's see the two charts here. The blue line is the batch normalization, and the green curve is the instance normalization. So from here, you can see they report use instance normalization can improve the optimization process for texture transfer better than the ones used for batch normalization. Okay, so that's the papers use instance normalization to improve their optimization process. There are some results from the paper. Okay. So this is who? Peter Bryan, right? Okay. And their method can transfer the image to other sets. So this is a comparison. The first column is the input image. The second column is their method. And the third column is also their method, but use batch normalization. So here, if you see the quantitative comparison, instance normalization is better than batch normalization. If you see the qualitative comparison, they claim instance normalization is also better than batch normalization. Okay. So you see, batch normalization is very useful to train a classification network. But however, for different tasks, there may be some different or better choices you can try. Okay. All right, so I'm going to the second topic about Yolo. Okay, because I see one of your classmates use Yolo V5 to do his homework 3, okay, and he found the Yolo V5 cannot detect some artifact on the road, and the reason is, do you know the reason right now? Okay, never mind. And another classmate used Yolo V8 to detect helmet, all right, but there's something wrong, okay. And I asked them, what's the difference between Yolo V5 and Yolo V8? And I would like to figure it out. So I go through those papers. Those papers are all Yolo Family. So the first paper was published in 2005, and the latest, let's not latest paper is Yolo V7. Okay, it was published in CPR this year. So you can see very new because CPR was held in June, right? And now it's November, just 5 months ago. So it's a very, very new paper. But I'm not sure whether the paper was uploaded to archive somewhere. Okay. And let me draw a figure like this. So this is Yolo 1, 2, 3, 4, 5, 6, 7, 8. Okay. So first 3 papers were published by University of Washington. Okay. And then the first author, he no longer did research for this topic, and I don't know why, and I couldn't find any information about it. Okay, the second group is Academia Sinica in Taiwan, and if we call it in Chinese, we call 中央研究院. Okay, and they published 4 papers, and this is Yolo. It is a representation. It's not a classification algorithm. It uses the idea of Yolo to extract image features. Okay. So that it can be used not only for classification, it can be used for some segmentation and image retrieval, etc. Okay, and the S4 means scale the Yolo V4. So let's take a look. This is the scale. Okay, scale the Yolo V4. So because I didn't read the paper thoroughly, so I don't know what to mean scale the Yolo V4. From the title, usually it means how many classes can be detected by Yolo V4. Maybe 1,000 or 10,000, I don't know. But the scale of the Yolo V4, if I just take a look of the title, it gives me a hint. Okay, maybe they can detect 1 million or 2 million classes. So if it is true, then it will be very big improvement. Okay. And this is a 7, right? And the Ultralytics is a company. So it modified the Yolo V4 as a Yolo V5, and they claim the performance was improved. And then you see there are some small circles. This means Yolo V5 version 2, Yolo V5 version 3, Yolo V5 version 4, etc. So the latest one is Yolo V5 version 7. And then it's become Yolo V8, right? And the Yolo X, it was released by MakeV. MakeV is a Chinese company, and its Chinese name is 旷视科技. Okay, so if we turn the Chinese into English, it will be the excellent vision company. Okay, so maybe it is a company focused on computer vision, etc. But however, it's just released a version of Yolo VX, and there's nothing more. We don't know what happens there. And the Yolo V6 was released by Meituan. It was also a Chinese company, Meituan. I'm not sure what is the business about Meituan. It's an online store or something else? I don't know. Okay. Oh, etc. No, okay. At least after reading this paper, you can know, okay, there are 5 different teams. They release the modification of Yolo. And okay, let's take a look. So I cropped the image from Yolo V8's official website. Oh, let me mention another thing. The Ultralytics company, they released, you see, there are 9 versions of Yolo, but they never published a paper. This is very interesting. But however, they release a lot of Python packages. So it's very easy to use their algorithm. Just import the package and then you can run. So, if you are interested in the theoretical improvement, you may need to read the papers. But if you are just in using the technology, maybe Yolo V5 and 8 are good choices because you don't need to know too much, and you just know, oh, they keep improving, Okay, so this is a comparison chart I crafted from the Yolo V8. Okay, so this is the performance. Okay, the higher the grade, and the Yolo V8 they claim. Okay, there are 5 different models. Small, medium, large, and extra large. What is the new? I don't know, tiny or something else. Okay, for larger models, the performance is better. But however, because there are more parameters, it takes more time to generate the result. So you can see the latency will be also greater. So this is a different curve. However, they want to claim, compare with other Yolo models, they are the best. So this is Yolo V7, and this is Yolo V6, and this is Yolo V5. Yolo V5 from they're saying that the same company. So if the curve towards the left top point is better, okay. So this is another. Okay, this is the number of parameters. So you see the tiny model has the latest number of parameters, and the large is around 66 million parameters. Okay. But however, this chart was cropped from their official website, and I found another chart. Okay, this is another chart. Okay, and then there are also Yolo V. This is V5. This is V7, and 8 is here, and this is V6 version 3. Oh, so from this chart, which is better? It's like V6 version 3 is better than V8. So there are something unsure, or I don't know which is. And take a look of the 2 additional charts. Okay, they are even better. And why? Okay, so let's see. So you can see there is a term NAS. Do you see the NAS? Okay, the NAS means they use algorithms to automatically tune the hyperparameters. Because when you train a neural network, there are many hyperparameters. How many layers are there? How large of the resolution for each layer, etc. So the company, okay, DeSi, the company, I think they are a software developer or something else. Their algorithm can automatically tune the parameters. Try this, try that, try this, try that, and okay, because they try a lot of hyperparameters, they can find a setting which is better than the original setting. Okay, so as I said, the NAS is network automatic search or something else. Well, okay, let's see. What is the full name of the NAS? Got it? Network. Right. Network architecture search. So because after paying time and effort to do the search, they find a better setting for the architecture of the network. And the next is also active research, because you see it's very useful. Okay. All right. Okay. Now we are going to the third topic of our homework 3 feedback. It's been convolutional neural visualization. So what is this? Okay. Let's recall your memory last week. So one of your classmates report this. It means this is the input image, and you see the heat map here. Okay. So the heat map means you can know using the heat map to where the convolutional network pay attention to. So for those vegetables or for the apples, yes, they see, okay, they pay attention to the apple. And for those vegetables, they pay attention to where and how to do it. Okay. The first paper of the heat map was proposed by okay, I should say, okay, the slide was used by your classmate last week, okay, and the first method to generate the heat map called CAM, Class Activation Mapping, and the idea is simple. If there is a convolution layer very close to your class scores, and then you can calculate the weight and sum them up as your classification. So this is the idea. I will show you some details later. Okay. So it means, given a neural network, if this is a classification or the network, then given an image, they are layer by layer, and finally we will get a score for every classes. And then remember, there I show you a slide why we need to use one-by-one convolution. The one-by-one convolution was proposed by the paper Network in Network. Okay, and in the paper they proposed 2 components. One is the one-by-one convolution, and another one is the global average pooling. Okay, so pay attention to global average pooling and the one. Oh no, I should say. Okay, let me show you the relation between it. Okay, so you know the one-by-one convolution is can be replaced the fully connected layer. So to reduce the number of parameters and accelerate its performance. And another one is the global average pooling. It means when you use many one-by-one convolutional layers, at the end, you will generate a set of image, feature maps. Say if you for CIFAR 10, there are 10 classes. So you create a layer. There are 10 channels. So and each of the channel will be summed up to become the final class score. So the operation to use the channel is just very simple. Average them. On the layer you have no matter how many values, just do global average. So this called global average pooling. Do you remember the max pooling and the average pooling? So or minimum pooling. So the global average pooling for the whole layers compute the average and become a value. Okay. So here, let's go back. If we want to show their mathematical expression, it's like. So this is the last layer of the convolution. So there are k channels. Channel means the number of your classes. And for each channels, the width and height are H and W. So global average pooling means you will average the whole images into just a single value. Okay, and then there is a fully connected layer. And then there is no activation function. You just weighted sum each of those values become your final class score. Okay, so the mathematical expression for class average mapping is just compute the mean. So suppose this is a three-dimensional column. The value is f, h, w, k, and k is number of channel. So it means we just for every channel we will compute the average of those values. So you will have k fk number. So this is the fk. Okay, and then there is a group of weight. This is wkc. We use the group to do the weighted average. So for each of element in the k vector, we do weighted average to generate the score. Okay. So by definition, you will just expand it. Okay. And then change the notation. For this part, okay, it is we just call the matrix here the class activation map. So let's go back to the slide. It's just like that. We have the many values in the last layer, and we learned a group of weight parameters as W here, and we just tie the W to its corresponding layer. So this is the first layer. This is the second layer and the second weight, and we get a group of layers and their weight become our class activation map. So what can we do for class activation? So this is usage. Say this is a CAM map for this input image, and because the image is trained on ResNet, say ResNet there are 1,000 classes, and we know the scores for each of the classes, and we pick up the top 5. So for the input image, for the palette class, the score is 0.59. For the Gung, so the score is 0.1. And for the 5 classes, we extract its CAM layer. So you can see this the result. So it can help us to understand what the network sees. Okay. So this is another example. There are 3 different dogs, and if we use the CAM technique to extract the class of Briard, okay, then we will see what are the convolutional network see. So for this image, he see this is the breed of the Briard, because he see the head. And for this image, he see the nose, and for this image, he see the head. It means from this image, for certain classes, this is most important part, and all other parts you may, they are less important. Okay. And so for the set of images, for the class of barbell, what is barbell? You see, there's there is a barbell, and this is another, and this is the important part is the iron, I should say, plate. Okay. All right. So because there are many different convolutional networks, AlexNet, ResNet, GoogleNet, etc. So with this CAM, you can compare what are the biases for those networks. So see, that's the GoogleNet. So if you see, this is GoogleNet, but there's a dash, GAP. It means they slightly modify the GoogleNet because GoogleNet, the original GoogleNet doesn't have the last layer for the, this layer. Okay, the networks, they don't have this layer. So they need to slightly modify the original GoogleNet to insert this layer so that they can generate the CAN layers. Okay, and the VGG the same. VGG don't have the CAN layer, so they need to add it. And Alex add don't. Therefore, once they add those layers, they will see, okay, what is the attention of the layers. And the table shows the quantitative comparison. It means if the GoogleNet, if they use the GoogleNet to train the ImageNet, then the error rate is 11.3. But if they slightly modify the GoogleNet and train the same image set, data set, then their error rate will slightly increase. Okay, so there is a trade-off. If they want to see what the attentions are, they need to modify the network, but they will reduce the performance. And not only GoogleNet, VGGNet or AlexNet all have the same phenomenon. This is 19, it become 20. And this is 11, it become 12. It will pay the cost of 1 to 2% performance loss. Okay, so 1 year later, another team proposed the Grand CAN method. It can overcome the problem. Okay, so how did they do? They can just pick any layer, and if the activation means the output result of the layer, it is R times W times K dimension. Then you can, because we know how to compute a gradient by backpropagation, right? So for a class score, we can compute its backpropagation gradient to the activation. Then we will get, this is also an R, it's a H times W times K dimension. Then, okay, we use the idea of a global average pool to this gradients, okay, and use a redo to suppress the value less than 0. Okay, and this is the result. So, given this input image, okay, this is their result. If they want to see the class of cat, then they see this is a heat map. And if they want to see the class of dog, and they see this. And the guided backpropagation is another method. But their method, because they can generate a high resolution image heat map, so they can combine the two methods. This is their method, and this is another method to generate the guided gradient CAN. It's just to do a simple multiplication. This is the heat map and the time pixel by pixel to so they can generate this guided gradient. And this is another method. It means once training the network and give the image, they can crop a region, and so they will see what is the effect of the cropped region. So this is the generated output image. It is much, I should say, blurred. And the author of this paper, they want to claim their method can generate a similar result as the occlusion map. See, because this is their attention, and the occlusion map also show this is the attention region. So they want to claim their result are as good as the occlusion map, but their methods are easy to use. In addition, their method not can be applied for classification networks, also can be applied for image captioning. So this is the image captioning case. Given an input image, they want to generate a sentence to describe the image. So this means image captioning. So once they generated a sentence, a group of people flying kites on a beach, so their attention will be the kites and the group. This is another example. A man is sitting at a table with a pizza. So the Grand Can method can show the attention of the sentence is the man and the pizza. Okay? So Grand Can improved the existing can method in the 3 ways. First, it can be applied to any layer. Okay. Second, it do not need to modify the original network. And third, it can be applied for image captioning and VQA. Oh, sorry, this is a typo. VQA network. VQA network means given an image and ask a question. You want to provide a correct answer. Okay, so here, when you do the homework, you have no idea why my Yolo v4 doesn't pay attention to the object I want it to detect. Now, if you know there is a method called GradCan, you can try to use GradCan to learn, okay, what's the problem of my Yolo v5 model. And also, you can apply, if you want, to insert the GradCan to your own models to know what's the problem or why my models doesn't pay attention to the object I want. Okay. All right, so let's take a break. All right, so most of you did your homework 3 for image classification, etc. And I want to slightly go further. Let's go to the action recognition because it used 3-dimensional, I should say 3D convolution. Okay, so 2D convolution you are very familiar with, and there are also 1D convolution. So it just means that, so this is the 2-dimensional space. If you assume the edge is just 1, it becomes a 1-dimensional. Okay, so the height of the images just become 1. And you can also apply a convolution. It becomes a 1-dimensional convolution. Also, if you have 3-dimensional data, means like in videos, you have width, height of the image, but you also have several frames. So it becomes a 3-dimensional data. Then you can apply 3-dimensional convolution on the image data so that you can do action recognition. And the first paper of 3-dimensional convolution, it was published in 2010, even earlier than the famous AlexNet, because AlexNet was published in 2012. Okay. And let's take a look of the 3-dimensional convolution network. It means given an input video. Okay, the video, there are only 7 frames, and the size of the resolution is only 60 by 40, so it's very small. Okay, then here, the authors convert the input videos into gray. So since there are 7 frames, so there is a group of features of gray. it's just convert the RGB layers into let's say grayscale layers, and there's also gradients along the x-axis and a gradient along the y-axis, and upflow along the x-axis and upflow along the y-axis. So here in 2010, you still see the approach use man-made features. It is learned by a neural network. Okay, then from this layer, it uses convolution. Okay, and the convolution for the 33 layers, it becomes 2 branches. It applies a 7 by 7 3D convolution. The 7 is height, 7 is width, and the 3 is the number of friends. Because the 5 group of data are different, so it applies the 3 dimensional feature to each of the groups individually. Therefore, you can see there are 7 friends for the gray. Apply for the 3D dimensional version, there are only 5 friends for the gray, and also 5 friends for the gradient x, gradient y, and 4 for the optical x and optical y. Remember, when you apply the convolution layer for 2-dimensional measures, if you have no padding, then your feature map will slightly shrink. The same for the 3-dimensional space. Because it applies 7 by 7 times 3, and the authors didn't use any padding. So for the image resolution, it has become 54 times 34. Original was 60 by 40. So for the image plane, it is shrinked. And for the friends, it also shrinked. Okay, then apply a 2 by 2 subsampling and apply another 7 by 6 by 3 set new 3D convolutions and do it several times, and then they see there are only 1, 2, 3 classes. Okay. So what 3 classes do they use? They use this data set. It's called track with 2008. So there are only 3 actions. Cell to ear, it just take a cell phone to your ear, and the object put, those subjects put an object, and the pointing is raise your hand and point to somewhere. Okay, so the data set was released by NIST USA. NIST means the National Institution of Standards and Technologies. Okay. There's another famous data set called MNIST. Do you remember? The Alex, Young LaQuinn. He developed the convolutional networks on the MNIST data set. And 20 years later, he and other 2 researchers, one is Hinter, another one, they won the Turing Award 2008. Okay, the data set MNIST modified NIST data set. It was also released by this institute, NIST. Okay, and right. So let's see the property of the data set. There are 45-hour videos captured in an airport, and use 5 different cameras with the resolution of this. Okay. So they show their results. Use the 3D convolutional method on the data set. So here you can see for the 1, 2, 3 actions, their result performs very well to the cell to ear and object put action, but didn't perform as well as the 2D convolutional network. However, their average scores are best. Therefore, okay, they show the value of their 3D convolutional networks. And they also did their experiments on another data set called KTH action dataset. There are only 6 actions. They are walking, jogging, running, boxing, hand waving, and hand clapping, right? Okay, the dataset was composed by 25 subjects, and there are 4 scenarios: outdoor different scales, outdoor different qualities, and indoor. So this is spec of the dataset, and also they show their result. But however, okay, this is their result. The average is only 19.2. It is not as good as other state-of-the-art in 2010. So let's take this chart. This is the chart cropped from our textbook. The paper is published in 2010. They are still using the classic machine learning pipeline because they use hand-created features. The gray and the gradient x, gradient xy, optical flow x, optical y. And 2 years later, AlexNet showed the power for this approach. Okay, so of course, see, in 2010, 3D convolution has been used. Although, okay, there are some other better performance, but right now, almost every action recognition algorithm is convolutional based. Use convolutional network to extract the important feature. And let's take a look of the state-of-the-art action recognition dataset. This is 5Gen. It was published in CPR 2020, and it is an oral paper. And okay, I think let's take a very quick look of.
Here I will present our work, FineGen, a hierarchical video dataset for fine-grained action understanding. FineGen focuses on gymnastic actions, trying to review the gap between coarse and fine-grained action understanding. Annotations of FineGen are in 3 semantic levels and 2 temporal levels. Specifically, we provide temporal locations for each action instance and its event label. We further divide it into sub-actions, providing site label and element label. FineGen is distinguished due to its high quality and rich annotations and its action-centric video data. Here are some analysis and findings. Sparse sampling struggles on FineGen, indicating every frame counts. Temporal modeling matters for fine-grained recognition, motion-intense actions. Pre-training on coarse-grained dataset may not always be helpful, and FineGen poses new challenges for current methods.
Okay, see, there are 4 different actions. Let's see. 5. Vault, uneven bars, balance beam. 4. Okay, this is floor exercise. There are 4 different the basic classes, and under different classes, there are furthermore fine-grained. Okay. There are a lot of fine-grained actions, and the dataset is very large. So overall, there are 288 actions, quite large. So, okay. Right.
Divides into sub.
All right. Another state-of-the-art dataset for action recognition is the NTU RGBD. Okay. The NTU is National Technology University at Singapore, and RGB plus D means it provides not only the RGB videos, also depth video. So here you see the 2 images. They are cropped from their depth video. Okay, and this dataset was captured in an experimental in a lab. So you can see there are a lot of lab chairs and walls, etc. And they also provide the annotation of a skeleton. So from this image, you can see their skeleton here. So the advantage of this dataset, it is very complete. You can have depth and RGB and the skeleton. So if you want to do any action recognition algorithms, this is the baseline. You almost need to, you can find anything you want to do your experiments. Okay, so this is their statistics. The dataset contains 56K samples and 60 classes. So compared with the 5Gen, there are only 60 classes, less than 288. And it is captured by 40 subjects from 80 view angles, right? And so compare some existing datasets is quite large in the year of 2016. And then there are some domain-specific action datasets. So this is SUEND dataset. It was just released in this. Why are you smiling? Oh, really? Oh, interesting. Okay, yeah, it's very similar. So the SUEND dataset, it was there are 10 actions in a gene, the square and something else. Okay, it was very new. And the BabyNet, okay, the BabyNet, it was an archive paper, but and let me show the statistics. The data is very small. Let's see, there are only 193 clips. And the action defined in the data, there are only 2 actions. It means the baby uses his or her left hand to touch a parent. So the data is very, very simple. Okay, I think this is the reason why it was only uploaded to archive and was not accepted by any conferences or journal. But this is interesting. And I know there is something interesting. The National Taiwan University Hospital, they are compiling another data set. It means they are baby, they will crawl somewhere. And they use cameras to capture the videos so that they want to train the network to predict whether the baby is very healthy. There is AIMS scores, okay, to indicate the developed level of the baby. Okay, so that's what they are trying to do right now. Okay, now we are going to some slides about your homework 4. As far as we go, you learn a lot of discriminative models. It means, given an image, you want your models to know whether this is a cat or dog, or it is a car or a helmet, okay, or vest. So this is discriminative models. Given an image X, you want to predict what the label of the image is. And then your homework 4 is going to do generative models. It means you want to give a label or something else so that you can generate an image, just like what I do. And okay, how to do it? So there are some mathematical description. So given an image X or given an image data, how do we know it is an image or not? Okay, so if you see the television, and if you unplug the cable of the television, you will see a lot of noise on the television. Those are also images, but you won't see this is natural images or image you expect. So that's the case. Given any image, you want to predict the distribution of the something you want. So suppose we have an X, then for any kind of images, their summation their probability of the images, as I mentioned, is 1. Okay, and for our discriminative models, okay, we given an image X and want to predict whether there is a cat, or is the image belongs to a cat, or is the image belong to a dog. Okay, and given another image, we want our discriminative model to do the same thing, but based on the content of the image, we want our model tell us, okay, the probability of the image is a dog should be higher, and the probability of the image is a cat should be higher for this case. So it means the model will compare those images to generate the probability of the label. And the model has a restriction. If it has never been trained for certain classes, then it can still generate a probability, but it is meaningless. And we can even give the model some images. It is meaningless, but it still will generate some scores. Okay. So, however, this is the discriminative model. And for generative model, it means our model will generate some images, and we would like to know whether it is the images matching the national image, or whether the image data is the the data we want. So there is another probability. So this, okay, it looks like an image, and this is also look like, and this is not the natural images we want. So it will generate a very low score or low probability. So this is the model we want to train. And if we can train the model well, then we can use the model to reject some data. They do not look like a natural image. Okay. And okay, so for our homework 4, what we want to do is we want to give a label or something or condition. We usually call it condition. The condition can be a label, can be a text prompt, or just another image. Okay, we want to use the condition to create another image, right? So use the Bayesian rule. Given a label or a condition, what's the probability of the output image? It will become the probability of the label and the probability of whether it is an image times the given the image and its conditional probability on the label. And so this is a conditional generative model, and that's what we want to do for our homework 4. And then this is a discriminative model, and what most of you try to it for your homework 3. And this is the generative model, and this is prior over the labels. Okay. So for your now you have the experience when you have the data, so you can assign the label to your data. Okay, it means you use neural network or the handicraft features to describe the image, so that you can use some machine learning algorithm to learn whether this is the image with the label. And the generative model means we want to train something so that the model can generate images with the probability we want. Okay, and the conditional. So we want to given the label at first, then the model can generate the images. So okay, this is our Kubeflow system, right? And you can insert or key in some text prompt. So here, let me see whether it's alive. Okay, it's alive, right? So here, okay, just like the demo, and I will try to do it again. So here, this is a prompt. Prompt is our condition. I should say, no, all of you can enter anything. The prompt enter, and ask the system algorithm to generate the images. So this is the condition, and there will be some images generated. Right? So let's see. Take a look later. Right? And you can also add some more conditions. So like this one, okay. If we add a children's drawing style, then we will get another output images. So this is generative model. And okay, let's see whether the image was generated. All right. Okay, so we generated the images, but there's something interesting. So this is a hamster with a hamster's head with a goldfish's body. Fine. And right, this is a hamster and a goldfish. All right. Okay. So at least okay, it works, but the output is weird or funny. All right. So okay. What I want to show is you can. So there are many conditions. Now let's take a look at how do those images are generated. The research for generating image has been started for many years. Okay, and there are a family. Okay, so there are two branches. First, can we calculate the probability of the image? One approach is let's try to do it. Another is no, our models, we do not or cannot to calculate the probability of a data, whether it is image or not. And okay, there are also two branches for the explicit density approach. One is yes, we want to build a model. Then the model can exactly compute the probability of the image data, or not the image, just pixel by pixel. If I can just given a region and want to predict the next pixel, it's fine. Okay, this is also an image model. And another one is I have no way, but I can approximately estimate what the probability is. Okay, so the variational autoencoder, okay, goes to this approach, and the Markov chains go to another approach, and our GAN, okay, is here. For GAN, it doesn't explicitly calculate the probability of image, but it assumes we can sample. Sample means we can collect a lot of images from distribution. Okay, so variation autoencoder and the GAN are still widely used for state-of-the-art image generation model. Then take a look. Okay, this is our model. All right, so if you take a look of this user interface. Okay, you see there is a customer VAE. The VAE means variational autoencoder, so it is still used. You can turn it on or off, okay? And if you see gain, so here, fix incorrect face and eyes, it's used again. So if you turn it on, and there are several options you can use. And scale up, okay, the default method is also used again. So there are several, they are also gain. Okay. And let's see, all right, okay, so let me show an example, okay. Let's see, okay, how to spell my coach AEL Jordan and generated 4 images. I don't know whether the model knows Michael Jordan or not. All right, okay. Yes, he knows. At least he knows he's a basketball player for the Bull teams, and the number is 23. But I want a face. Let me try another step. Face. Alright, so, alright, okay. There is a face, but it doesn't look like Michael Jordan. However, okay, you can see this is a click called fix face. If you click here, okay, and let's take a look of his face. What's the difference? Okay, it take a while. Alright, okay, let's go back to our site and see our results later. Okay, see, if I use Stephen Curry as an example, okay, then you will see the customer VAE and the correct face and eyes used again. And, okay, so if this is the image generated by the Stable Diffusion, and if I use the GFP GAN, okay, you will get another image. The only difference are on the face region. And if I enlarge it, okay, so this is the original one. This is the image modified by the GFP GAN. And there is another GAN called, let's take a look here. All right. This is the scale up option. It is used, it calls the real ESR GAN. Okay. And, okay, let's see the difference between the undo and the fix redo. Okay. Well, I didn't see the difference very much. All right. Okay. So if this is the image with the GFP GAN, it will help you to revise the face region. Okay, so you can see slightly better result here. And if we use the real ESRT GAN, okay, it is something like a super resolution. You will create a resolution. So this is for this image, the data size is only 173 by 203 pixels. We show it on the screen, use PowerPoint. PowerPoint use particular integration or something else to enlarge the image. And this is the result with the real ESRT gain for 4 times super resolution. So for the details, you see it's much clearer from this one. Okay, and we are going to right. Okay, so you see the name. The name is GFP gain. So what is it? Okay, so this is a paper toward real-world blind face restoration with generative facial prior, and published in CPR 2 years ago. It's a very new paper. And this is the result shown in their paper. So this is the input image. Some of them are grayscale, blurry, or a lot of noise. And this column shows their results. So this is a restored face image. They only work for face images. Okay. And they compared some existing methods published in 1 year ago CPR or 1 year ago ECCV, okay, or ACMMN. This is I remember the ACN, American Computer Community or something else, and the multimedia. So, okay, then so this looks good. And what is why it works? Okay, so let's take a look. So this is again structure. It means there are at least two neural nets. One is the generator, another is the discriminator. So this is the generator part. They have many paired image, means low resolution blurred noise image, and high resolution, high quality images. They train their networks using those pairs of images together. And this is generator. The generator learns when I see a low resolution noise image, what parameters I should learn to generate the high resolution image. Okay? And there is also a discriminator. Discriminator means this is a generated image. So let's go back to the gain. The concept of gain is I don't know what is the real probability of those images. I can collect a lot of samples from the probability. It means I can collect a lot of samples from real image. So in this case, they need to prepare a lot of face images. This is the samples for gain. So they train the generator and train the discriminator. So here, they have not only one discriminator. They have multiple discriminators. The discriminator will tell whether this is a generated image or this is the real image. Okay, so the real image is the sample, and the generated image are generated from the generator. Okay, and okay, I just want to show you some concepts, and we will go to the details later. And then, okay, so the real ESRT gain, okay. So these are two papers. This is the paper, GFP gain. It was published in CPR 21. And this is the high resolution gain. We use both of them in our Stephen Curry's example. Real ESRT gain, it was published also 2 years ago, but it was published in the ICCV workshop. Okay. Usually, for a conference, there is a main program. The best paper was published in the main program. Okay, it will be ICCV, International Conference on Computer Vision. And there are also many workshops. Workshops, they have their own interesting topics. And for this workshop, they submit their paper. Usually, those papers do not have as much contribution as the papers for the main conferences. But some of them are still very useful, like this one, real ES-GAN. It was not accepted by the main conferences, but only, okay. And there's a timeline. Usually 3 or 4 months before the conference, authors submit their papers to the main conference. And then after reviewing, they will receive a notification whether your papers was accepted or not. If their papers was not accepted by the main conference, they can submit to the workshop, and they still can get a chance to be published. So I am not sure whether it's this case, but however, I say the super resolution GAN, okay, they show their result here. They generate images quite good. Okay. So this is their real ESR GAN, and there are some existing methods, means real SR and ESRG GAN, and this is the result generated by cubic interpolation. So bicubic interpolation is a very simple, just use a curved line to fit in, so it's very blurred. Once we see the result, you can see for the eyebrows very blurred, but this is generally good. And okay, so for this paper, real ESRG GAN, this idea is quite simple. How simple should I say? Okay, it means there are 2 existing methods called ESRG GAN and the real world, the real GAN. Okay, and the author of the real ESRG GAN, in fact, is the author of the ESRG GAN. So, and you can see the ESRG GAN was published in ECCV 18. So this is the new earlier paper. And 2 years later, there's a paper, real GAN, published in CPRW. Okay? And the author found, idea is interesting. I just borrow this idea to train my GAN network. So the real ESRG GAN, the real means it borrows ideas from the real GAN and apply the idea to its own method. So it becomes real ESRG GAN. So what's the idea? The idea of a real GAN is, because there are many different types of degradation for image. There are downsampling, there are noisy, there are JPEG artifacts. Okay, so I don't know what the model should be. So how to do? When I have a high resolution image data, I generate a lot of different kinds of low resolution images, noisy data. And I use those training samples to train a comprehensive model. So the model can deal with any kind of degradation. So this is a real GAN. Okay, so in the real ESRG GAN, they propose the training method. It means given a high resolution image, there is a blur step and a resize step or downsampling step, and a noise step, and they also add the JPEG compression artifact. And they not only do it once, they do it twice. Add blur, resize, noise, and the JPEG artifact again. So they generate various low resolution, low quality images, and they use the images to train their model, to train the existing ESR GAN model. So they generate results better. Okay, so to understand the generative, the versatile network, the GAN, okay, you can take a look of our textbook. In chapter 5.5.4, it's very, very short, just a very simple section. And the section covers 2 topics. One is variant autoregressor, and another is GAN. It shows a very, very high-level viewpoint through the GAN algorithms. So in the textbook, you can find this figure. So it shows 3 different types of GANs. The first is the simple GAN. It means there is only one input. The input is latent code, or just you can imagine noise. They use noise and a generator to generate images, and there is a discriminator, and the X means real images, the real world image. So what they want is to generate the image, use a generator and use a discriminator to tell whether the images are generated or real. If the discriminator cannot distinguish this is real image or generated image, then okay, it means the generator is good enough to generate realistic images. And the second chart is our homework 4. It means we have many conditions. Our conditions will be used to influence the generator, so that we have some images not only generated by noise, but also by our condition. Okay, and let's take so the idea of GAN was proposed by Goodfellow in NIPS 14. And who is Goodfellow? Goodfellow is the author of our reference book. Okay. And these are the results proposed by his method. So this is N means typo. It should be N NIST. And there is another TFD dataset and the CFAR10. You are familiar with it. So in 2014, Goodfellow's method can generate those images. So this column is the ground truth images. Okay, and the same. This is the ground truth, and these are images generated by the first GAN algorithm. It's very simple. And then 2 years later, there is another method called DC GAN. Okay, the DC GAN uses the convolution network. So the convolution means it's something like the inverse of subsample. You know pooling, right? Max pooling or average pooling. It will reduce the size of the image. And the convolution, it in fact is something like upsampling. For 1 pixel, you can upsample several pixels to the new layers. So so that you can see it become larger and larger. So this part, if you know UNet, okay, the second half part of UNet, in fact, is the convolution layer. So the image becomes larger and larger and larger and larger. So DC GAN can generate images with a larger resolution. Okay? But however, it is still a simple GAN. There is no condition. Although, so they use the LO-SUM dataset, large scale scene understanding set, and there is subset for bedroom. They train their models use the bedroom, and they generate images that looks like real images of bedroom. But however, there is no condition. You cannot control anything on the network. And 2 years later, there is a GAN method called star GAN. This is the conditional GAN. Conditional on, okay. So conditional on this is the input. This is the first condition. And the second, there is a label. Blonde hair, gender means male or female, age or not age, and palm skin or not. So you have 4 options. Age, whether the hair is blonde, young or age, and palm skin. So given an input image and the label, both of them are conditioned. The the model can generate different outputs. And for this is, again, given an input image, and there are 3 options, there are conditions, angry, happy, or fearful. Then you can also generate different output images. So here is the conditional GAN. And let's take a look of the architecture of the star GAN. So here, this is a discriminator. It is used to tell whether the image is real image or generated images. And this is the generator. So in fact, the generator is a cycle GAN. It means for an input image and a conditional label, it will generate the output image. And then use the generated image and the original label. The original means, okay, if this is a male image, male label, okay, and I use a female, it will generate a fake image. And then I use the male label again. It expects to generate the same image back, so it means a cycle GAN. This is published by another paper, and something interesting is, in the beginning, in the GAN, it was published in 14, right? And it a lot of GAN was published. And somebody wants, in the beginning, he wants to list all of the GAN. And he did it for a few years, and finally he gave up. Because there are too many GANs available in the world. Okay. For example, we see star GAN, and 2 years later, they published another star GAN V2. Okay, then some modification, and results. So they compare their previous one and the new one. They show, okay, the new one is better because they do some modification for their architecture. All right, so let's stop here, and next week I will try to cover the content of stable diffusion. So the easy diffusion, when you see the interface, it combines stable diffusion model and the GAN models. Okay, so next week I will try to cover it. So help to understand, right?